All right, hello. So as it relates to Design Project 2, a classmate had a question about modeling ammonia synthesis reaction using an equilibrium reactor in CHEMCAD. And so the main challenge is converting our equilibrium constant or getting our equilibrium constant set for use with an equilibrium reactor in CHEMCAD. Okay, and so the challenge uh, so hold on, my face is in the way. How do I get the help back up? So let me just double click on the reactor. So the challenge is when I go into my equilibrium reactor, my equilibrium constant is modeled as such. Okay, and so what I need is an expression for my equilibrium constant that takes the form of log k is equal to a plus b over t plus c natural log of t plus dt plus et squared. Okay, cool. Now the challenge is when I search the literature. So here I was doing a Web of Science search, right, for ammonia synthesis. And this is the paper I had in that last video, which includes an expression for the equilibrium constant. Right, beta is just a constant, and they say it's this Gillespie-Beatty equation, equation 20, or reference 26. But the key is when I look at this equation, is it uses log base 10, right? And so I um, pulled up the Gillespie equation. And so how I did that is from the web version, I just, click the link to get to the Gillespie version. And so in Gillespie, we have this equation 19. So it's the same. It's just they have um, a value in there for what was beta, right, in the others. Okay. And so again, the challenge is here we have an expression which uses log base 10. I need an expression which uses natural log for use in ChemCAD. Okay, and so let's go through how we would do this. Okay, so what we currently have, okay, and so one, right, you'll see it has the same form, right? So it's constant plus constant over t plus constant times log t plus constant times t plus constant times t squared, right? So it's the same functional form. It's just here we're using log base 10 instead of natural log. Okay, and so we have log base 10 of k is equal to, and I'm going to write this as little a plus b over t plus little c times log base 10 of t plus little d times t plus, have e here, I'm going to write as a little f just because I'm going to use little e, right, in my conversion. Okay. Now the key is remember natural log, right, is log base 10, or log base e. So natural log is log base e. Okay, so converting from natural log to log base 10 comes up a lot. So in my background in thermodynamics, it comes up a lot in terms of functional forms of my Clapeyron equation and converting equilibrium constants, as we're doing here. And so how I've learned, or how I approach this, is I've just often I've just often gone to Purple Math. So Purple Math provides an expression for converting the base in our log expressions. And so the relevant equation is written from Purple Math is log base 10 of b of a is equal to log base x of a divided by log base x of b. Okay. All right, so now in our problem then, what we have is that natural log of k, okay, well that's log base e of k, which is natural log of k. So natural log of k is log base e of k, and that's going to be equal to um, log base, okay, 10 of k divided by log base 10 of e. Okay. All right, so what I'm going to do then is if I want to go from log base 10 to natural log, is I'm going to divide through by log base 10 of e. So that'd be equivalent to dividing little a by log base 10 of e, little b by log base 10 of e. Okay. um, little d by log base 10 of e, and little f by log base 10 of e. Okay, this term is a little different, right? Where this is different is that, well, when I divide this term through by log base 10 of e, okay, we actually have here log base 10 of t then divided by log base 10 of e, right, which would give us natural log of t. Okay, so let me try and make sense of this. Okay, so what I'll need then, okay, is big A. Okay, so I'm going from log base 10 of k to natural log of k of to natural log of k. Okay, to do that, I'm going to take log base 10 of k and I'm going to divide by log base 10 of e. Okay, so looking at the first term then, okay, big A is just going to be equal to little a divided by log base 10 of e. Okay. B is going to be equal to little b divided by log base 10 of e. Okay. C I'm going to come back to here in a second. Okay. Big D is going to be little d divided by log base 10 of e. Big E is going to be equal to what I was calling f divided by log base 10 of e. Okay. Now C is a little different, right? Why it's a little different is that if I have C times, and I already have log base 10 of t, and I divide that by log base 10 of e. Okay. Well, I also need to convert this log base 10 to natural log. Okay, and it so happens, right, that log base 10 of 10, or log base 10 of t divided by log base 10 of e, okay, well, that's equal to, c times natural log of t. Okay, so dividing through by log base 10 of e serves to convert that log base 10 of t expression. Okay, so big C, right, then it's just equal to little c, right? My constant in front of the log term is unchanged. The dividing by log base 10 of e, in this case, serves to change that log base 10 of t to natural log of t. Okay. So if I pop up MATLAB, okay, so now we're going to try and convert these things. Okay, so looking over here at Gillespie, so A is this first term. A is 2.6899. B is 2000. B is 2001.6. C is this term. C is negative 2.691, 2.691, 122. D is this one, so D is equal to negative 5.519, 265 e to the negative 5. And then F is this one. F is equal to 1.84, 8863 e to the negative 7. Okay. Now converting. Okay, so big A is equal to little a divided by log base 10, and how I get e is that's the exponential of 1. Okay, big B is little b divided by log base 10 of the exponential of 1. Okay, C I don't need to do anything with. Big C is just going to be equal to little c. Okay, but big D is going to be little d divided by log base 10 of the exponential of 1. And big E is going to be F, right, just so I didn't confuse anything with E, F divided by log base 10 of E. Okay, so now I've got my constants. Okay, and so then what I'm going to do is I'm going to go over to CHEMCAD, and to be honest with you, it took me a couple of times of looking at this to make sure I have it right. And so what we have here in table 3 is the Gillespie paper includes data. Um, so they have a feed, and this is the oh, but this is, I gotta look. I'm pretty sure Q and R are the mole fractions of hydrogen and nitrogen reactants. So Q is the mole frac of hydrogen, R is the mole frac of nitrogen. Okay, and then the other thing I just want to point out is, I should have pointed out before I started scrolling, is in our equilibrium so in our rate expression, where I find it, come on. So in our rate expression, pressures, the units of pressure are atmosphere, and the units of temperature are Kelvin. Okay, so when I come over to my reactor, so there was my information on my equilibrium constant. Okay, and so I had ran this one time just to make sure I had this working before I started recording. And so we have one reaction, general equilibrium reactor, vapor phase reaction. Okay, and I'm going to run it isothermally at 325. Okay, so I'm going to look at this, first condition here. So my feed stream is going to be at 325 and 10 degrees C, or 325 degrees C in 10 ATM. Okay. And then, we'll adjust my feed accordingly. Okay, but so here it's going to be run isothermally at 325. Okay, I'm going to specify an approach fraction, right? And so, kind of a reminder, because this came up the other day, is, okay, why are we specifying approach fraction? What does it mean? Okay, well, I'm going to specify an approach fraction of 1. And what that means is if I look down here under approach fraction, is it's equivalent to specifying that my conversion, right, is equal to my approach fraction times my equilibrium conversion. So if I specify an approach fraction of 1, that's equivalent to saying that, right, I have a conversion equal to my equilibrium conversion. Okay. So I'm going to specify an approach fraction. Okay. Then when I go into my reactor specifications, okay, my reaction is I have 1 mole of nitrogen and 3 moles of hydrogen reacting to form 2 moles of ammonia. In the Gillespie paper, they write it as 1/2, 3/2, and 1. Okay, but it's all equivalent. So I'm going to write this as, I have 1 mole of nitrogen reacting with 3 moles of hydrogen to form 2 moles of ammonia. Okay, your base component just needs to be one of the reactants. Okay, so you can choose nitrogen or hydrogen. Okay, so I had hydrogen here, right? It could be just select hydrogen or nitrogen. And then I need to input my constants. Okay, so this is just what I have here, right? So A is my 6.1937, B's 4608.9. Okay, so 4.6089 times 10 to the 3, so 4,689. C, negative 2.6911. Okay, C's unchanged. D, well, D is negative 1.2709. Okay, let me retype this one in just so you see it. Negative 1.2709. E to negative 4. Okay, I'll delete the 2 because in my abbreviated version I don't see the 2 here. And then E is 4.2572 times 10 to the negative 7. Cool. Okay, fractional approach of 1. Here's my stoichiometry. So if I go to my inlet then, okay, 325 degrees C. Well, 25 degrees C is 298 Kelvin. So if I add 300 to it, right, it's so okay, sorry, wrong tab. So if I add 300 to it, it's 598 Kelvin, right? And I should say I made sure my units of temperature were Kelvin and pressure atmosphere in line with the problem. Okay, I'm going to just say I have a total flow rate of 400 kilomoles per hour. It doesn't really matter. Okay, then here, this is my reactive gas. So there's my 2 mole fracs, so 0.762 and 0.235. Okay, then I'm going to just put a tiny amount of ammonia because I'm not sure what that these don't add up to 1, so I'll just make, a tiny amount of ammonia in there initially. Okay. But now if I run this, right, whoop, oh, now I broke it. So let me flash that. Let me click this and let's run selected. Oh no, I swear it was just working. So I'm going to keep it isothermal, 325, approach fraction. What happened? Okay. Let me change the base component to, it shouldn't matter. Hold on, now I broke it. Now I did it. Okay, so what happened? 6.1937, 4.6089 times 10 to the 3, negative 2.6911. D's negative 1.2709. Oh, this is e to the negative 4. Okay, so I forgot the e to the negative 4. And then 4.2572 e to the negative 7. Okay, hopefully now this will work. So click OK. Run selected. Okay, now it runs. Phew. So it was just I had a typo in my constant. Okay, if I look at my product stream, mole fracs. Okay, yeah, mole fracs are fine, right? So it's like 83% ammonia. Okay, cool. And that's at my 325 degrees or 300. Ah, my temperature's off. So this is 598. We're going to get this. So this, right, we said isothermally at 598. Okay. So running at 598. Okay, looking at my products. Right, here's my distribution. Let me convert this to mole fracs. Okay, I'm about 30% ammonia. So let's see, did it have it? Mole percent of ammonia in equilibrium mixture. Okay, this is about 10%. So it looks like we're higher than that. Yeah, we're about 30% is what we're computing. Oh, so let me just make sure we've got everything right. So if I come here, so we've got temperature in Kelvin, pressure in ATM, that's good. And then mole flows, right, those are just, moles, right, it doesn't matter which. Okay, if I change nitrogen to my base, right, it shouldn't matter. Yeah, it doesn't matter. And so if I change this to mole percents, all right, we end up getting 30% ammonia, so we have more ammonia, right, in that final product. Let's see what happens if this goes to 0. And let's make this 7. So what if we start with no ammonia? Okay, run it. Yeah, it's still about that 30% at equilibrium. Okay, and so I might need to investigate more, right, because this says this is calculated. So it's calculated when computed using equation 16. So equation from 16, when Kp is calculated using equation 18 and 19. All right, so I guess those values computed are based on 16. So yeah, so I guess these aren't exact equilibrium constant values that I'm computing. Okay, so looks like that works. Okay, and so if you were to try even for comparison, okay, let me try modeling a Gibbs reactor. Okay, just out of curiosity. Okay, so what I'm going to do, so my Gibbs reactor, I'm going to set up to be the same. We're going to be 598 Kelvin. 10 ATMs, and then let me get the compositions from the table again. 0.762. Oh, I need to make this mole percent. Seven six two. 762, and then 235. Oh, and let's just say this is 100 kilomoles. Okay, so run is 2345, 765. Yeah, so it's about exactly the same. Only now this is a Gibbs reactor. I'll run it isothermally. We're at 598 Kelvin. It's vapor phase reaction. And yeah. And so let's see what my Gibbs reactor says. So if I run this in a Gibbs reactor, I get, so let's convert this to mole percents. So this is kind of interesting. So my Gibbs reactor at 598 Kelvin and 10 ATM actually predicts a distribution very similar to this paper, right? So this paper suggests mole percent observed of ammonia, right, 10.38 at those conditions. Gibbs reactor gives me 11.239, right? Pretty darn close. Okay, whereas me with that equilibrium constant, I have something closer to 31%. Okay, let's try. Okay, so that's at 325. Okay, so here we're getting up to much higher conversions. Let's try 500 and 600 ATMs. So let's change this to 500. So it's going to be 773 Kelvin and 1000 ATMs. And we'll run it isothermally at 773 Kelvin. So if I run this, coming out, we're about 79% ammonia. Okay, I'm going to say 773 and 1000. Oh, and I changed it, 773 and 1000. If I change this to 773 and 1000 ATMs, running isothermally. We're at about 53%, right, which is pretty close to this. This is 42%, right? We're at 53, right? So it's, oh, and I went up to 1000, right? It shouldn't have went up to 1000. That's 100 or 600. Okay, so, all right, I'm going to try one more time just to see if I get closer. So changing this to 600, I overshot it. We're at about 39.8%, right? 39.8, right? Experimentally observed 42. Pretty darn good. Okay, and over here, so I overshot it. If I'm at 600, %, right? So, you know, my equilibrium reactor slightly overshoots. The Gibbs reactor is, you know, pretty close based on this. Okay, you know, I should probably look at this in more detail because it does look like I'm missing something, right? So this is based on, it's being computed using equation 16, right? I should read this. So they're using equation 16 to calculate those conversions, where alpha and R, right? Alpha is the mole frac of ammonia in the equilibrium mixture. Q and R are the mole fracs of hydrogen and nitrogen in the reactant gas. So Q and R, what's being fed in. Alpha is the mole frac of ammonia in equilibrium. And so they would solve that. expression using, well, I guess they first calculate Kp star, which is what I put in as my equilibrium constant. Then with Kp star, they would compute Kp. And then, this is Kp, right? So it looks like there's a little more to it. But I started with this equilibrium constant because I'm looking at this equation, okay, where Ka is the equilibrium constant, right? And the equilibrium constant comes from the Gillespie equation, which is exactly what's in that Gillespie equation, only the term in front of the log term changes slightly. Okay, so so here's me converting that equilibrium constant as is. Okay, here's me also using equilibrium or Gibbs reactor, and the results of the Gibbs reactor are pretty close to what was actually observed in that Gillespie paper. Hope that helps. If you need anything else, let me know.